today. Then we'll go to lecture and, call it a semester at that point, hopefully. All right. So we're going to talk about some stuff here involving organic chemistry. So basically, organic chemistry is the chemistry of carbon is usually the first sentence every organic chemistry book is. It's the study of basically carbon compounds and their sort of derivatives. The basics of organic chemistry is really the bond between, say, carbon and carbon. And attached to those carbons are basically hydrogens. That is the basic organic sort of connectivity that we have there. As we'll talk about here, obviously, as you should know, basic organic compounds are really going to be nonpolar. And that's because obviously the carbon-carbon bond is a nonpolar bond. And the carbon-hydrogen bond is also nonpolar. So a lot of organic molecules obviously are nonpolar in nature. There are different groups of organic molecules, as we'll talk about some different sort of groups, and they basically arise from really sort of the replacement of one or more hydrogens with other sort of elements along the way, things like oxygen, nitrogen, sulfur, and so forth. So as we sort of exchange some of these hydrogens out for other elements, it does sort of change some of the properties of organic compounds. There are some organic compounds that are actually polar in a sense because they can interact with water and soluble in water because of the sort of functional groups that they have. So really, there is sort of the beginning of most organic books. It's the study of compounds that contain basically carbon. Organic chemicals are in all parts of our life. Gasoline, oil, petroleum, all these things are really organic. Now, organic compounds, because they're essentially made up of all nonmetals, basically are covalently bonded together. And as you hopefully know, covalently bonded means that they are sharing electrons. Yes, so they are sharing electrons. And that's a little bit different than ionic compounds or inorganic compounds. Inorganic compounds or ionic compounds, there are no sharing of electrons, right? And basically what they have is the positive negative attraction, the electrostatic attraction between the cation and the anion that basically hold that together, as opposed to in an organic compound where we have covalent bonding, which holds everybody together through the sharing of electrons. So there definitely is some different properties. In most cases, a lot of organic compounds will be used in dispersion forces. And if you remember, when we talk about intermolecular forces, those are the forces that hold basically one molecule together with another molecule. And pretty much the basis of all intermolecular forces is the positive side of one molecule is basically attracted to the negative side of another molecule. And there's really three types of intermolecular forces that you talked about before, hopefully. There is hydrogen bonding. And hydrogen bonding is can happen when you have a bond between hydrogen and it is directly bonded to a nitrogen, oxygen, or fluorine. That nitrogen, oxygen, and fluorine are really, if you look on the periodic table, the most electronegative atoms there, right up to the right. That's going to create a really polar bond. And this is typically the intermolecular forces that polar molecules use that have obviously the ability to hydrogen bond. It is really a dipole-dipole interaction. But something like water, hydrogen bonds, right? Because water has more negative at the more negative at the oxygens and more positive on the hydrogen side of water. The next type of sort of intermolecular force is what is referred to as a dipole-dipole interaction. Dipoles, as you remember, arise from polar molecules. They have dipole moments, right? And that means that overall there is unequal sharing of electrons in the molecule. And this is really the major intermolecular force that polar molecules use that cannot hydrogen bond. And it is pretty much this attraction up here. The positive side of one molecule is attracted to the negative side of the other, and that is what holds those guys together. So if you had something like maybe CF3H, that would be a polar molecule. It does not have the ability to hydrogen bond. By the way, that hydrogen that's attached to the carbon cannot hydrogen bond because it is not directly attached to a nitrogen, oxygen, or fluorine. So it would do some type of dipole-dipole. Really, hydrogen bonding is a special type of dipole-dipole interaction. The last type of sort of intermolecular forces is what are referred to as dispersion forces. These are the main forces that hold together nonpolar molecules together. Because if it is a nonpolar molecule, it is sharing electrons equally, which means overall pretty much has no charge, right? So it's kind of neutral. Electrons are evenly distributed over the molecule. So dispersion forces are actually really temporary dipoles that occur. Perhaps you remember, maybe talked about it. There's really two ways that can happen. One way is what's referred to as polarizability, which means just by the electrons flying around, they could all end up on one side of the molecule versus the other, and it can temporarily create a positive side to that molecule and a negative side to that molecule, which is normally not there, but just because the electrons sort of moved around into that location, that then would allow it to sort of interact with another nonpolar molecule by messing up their electron distribution. And they both will end up with a temporarily positive negative sides of the molecules that allow them to interact with one another. Another way that you could do that is you can induce it, sometimes referred to as a induced dipole. And that could happen when you get a polar molecule near something that's nonpolar. If you pull a polar molecule near something that is nonpolar, the electrons in the nonpolar guy, which would be this guy, will decide to go that way. And then it will temporarily create this charge, and now they can attract to one another. So it's known as induced dipole. They're temporary because, frankly, as soon as those molecules move away, our electrons come back to their normal sort of spot, and they're going to kind of break apart their attraction. And that's different than in a polar molecule where no matter what you do to it, it always has a positive and negative side. So it's always ready to bond. It will never go away, no matter what the situation is. That's why when you mix things that are polar and non-polar for a bit, they can mix, like oil and vinegar salad dressing, right? They mix for a little bit, but eventually if you leave it, they separate out from each other, right? So, and that's because over the long period of time, they really don't have a way to interact with each other. So in terms of strength, as again, you may remember, hydrogen bonding is the strongest of the intermolecular forces, followed by our dipole-dipole, which is also relatively strong. Dispersion forces pretty much the weakest out of all of them. That's important because it is really the intermolecular forces that affect things like boiling points and melting points and those type of things. If you have a strong intermolecular force, would you expect a high or low melting point and boiling point? Should they be high or low? They should be high, yeah? So you should have kind of a high boiling point, melting point. That is because the molecules, right, are going to hold each other tighter, which means it's going to take more energy to separate them out. More energy to separate them out means you should have a higher boiling point and melting point. And obviously the weaker the intermolecular force, the lower you have for things like boiling point and melting point. That's why a lot of organic molecules are said to be volatile, which means they could go into the gas phase really easily because, frankly, they're not held together by very much. If you think about some of the early or lowest sort of organic molecules, those are things like methane, propane, butane, which you might be familiar with. Those are all gases under normal conditions because they're held together by really weak intermolecular forces. Also, if you plan on going on to what they call it here, Chem 80 organic, that's why they stick you in a fume hood when you work with organic material, because they very often just need to be opened up and exposed to air, and they can just jump into the gas phase really quickly. And a lot of them are flammable, which is why they usually stick you in a fume hood when you do those experiments, to prevent, obviously, any type of bad things happening. So organic compounds, because a lot of them are nonpolar, are mostly nonpolar, typically use a lot of dispersion forces, and those are really the weakest. So a lot of these things do have sort of lower boiling points and melting points and other things. Yes, sir. Mhm. Yeah, so there's other things like pressure and stuff like that that like play into effect in terms of keeping it in a certain state. But they're able to mix, just in general, they're able to mix because the like dissolves like, right? So you probably remember that. So nonpolar things and nonpolar things are soluble in each other. And obviously polar and polar things are soluble in each other. That's why water is not the greatest solvent, for example, if with organic compounds, because water is polar. A lot of organic compounds are nonpolar, so they really don't mix very well, which is why when you have like an oil spill, right, what happens is the oil floats on the water because the oil wants to use basically dispersion forces because there are carbons and hydrogens and nonpolar. Water wants to use hydrogen bonding. So over the long period of time, they have no way to maintain that interaction. Now, something that's ionic really uses really what is referred to as electrostatic attraction, right? Which is the positive negative attraction between the two molecules. And that's really more of an intramolecular force, right? And that's a really strong attractive force. Ionic bonding, covalent bonding, those are intramolecular forces, which are within the molecule that holds the molecule together. And those are always stronger than any intermolecular force that you have along the way. So all organic compounds basically revolve around carbon. Carbon has 4 valence electrons, which means in organic chemistry, carbon pretty much keeps going until it gets the 4 bonds. So carbon wants to get the 4 bonds in organic chemistry. As you also are familiar with, there usually is very few things. There are a few things, but mostly in organic chemistry, you don't see it. Carbon usually never has non-bonding electrons on it in an organic molecule. It can in other things, but usually it will continue to make actual bonds. That's really important because as you start to draw things that are organic and stuff, they like to just keep throwing bonds on carbon. And I've seen tests where carbon's had like 12 bonds to it. It just keep on like bonding, throwing lines on it. So it's a really important thing to remember. Carbon definitely wants to continue to make really 4 bonds. Carbon can form in organic compounds double bonds with itself, single bonds with itself, triple bonds with itself. And as you are aware, it will affect the geometry as you continue to make bonds. So let's take a look at just that idea here. If we have our single bonded carbon, which is not what I want to draw there, try that again. There we go. So something like this, which is basically known as an alkane. And an alkane is an organic compound that basically contains carbon-carbon single bonds. That is what is sometimes referred to as the functional group. So in organic chemistry, there's always a part of the molecule that is really kind of the important part of the molecule. It's the part of the molecule that tells you what type of organic compound you're dealing with. And that is really what's known as the functional group. And pretty much the functional group is where everything occurs. So in the reactions, that's pretty much the part of the molecule that undergoes the reaction is the functional group. So the functional group here for an alkane is the carbon-carbon single bond, which would be this. And if we look at this alkane, we could talk about a couple of things to throw back there to Chem 50. First off here, if I looked at this carbon right here, what would be the geometry of it? It has how many electron pairs around it? It has 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. 1 bond, 2 bonds, 3 bonds, and 4 bonds. Right, bond angle like 109.5 degrees. So in alkanes, because of the single bond, it makes a tetrahedral shape. In addition, the hybridization. The hybridization here would be sp3. Yeah, it's sp3 hybridized. By the way, if you're not sure how to do hybridization, here's a quick way you could do it. S orbitals have 1 orbital, p orbitals have 3, d orbitals have 5. And you basically count electron pairs like you're doing geometry. When you count electron pairs when you're doing geometry, double bonds and triple bonds count as how many electron pairs? 1. That counts as basically 1 electron pair. So if you have a double bond, a triple bond, or a single bond, it's all counted as 1 electron pair and 1 bond. So if we look at this guy has 4 electron pairs around it. You simply just count off starting with the S, 1, 2, 3, and 4. That's an sp3. That would be your hybridization basically right there. Now, this is also why when we look at alkanes, they sometimes are referred to as having a zigzag shape because of that tetrahedral geometry. If you draw something in line structure, which looks something like this, this is what is referred to as line structure. This is what is referred to as the expanded structural formula. In line structure everywhere, pretty much the line ends or it kind of makes a peak or valley. Those are basically carbons. So this is a carbon. That's a carbon, 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 and that's a carbon. That's why in line structure for alkanes, they are drawn sort of in this zigzag shape because of the tetrahedral geometry that is there. By the way, each of these carbons will have enough hydrogens to get carbon to 4 bonds. So the guy at the end would technically have 3 hydrogens. Guy in the middle there has 2 bonds coming in, has 2 hydrogens. All the way across here, this guy would have 2 hydrogens. And this guy would have 3 hydrogens. Again, in line structure, we typically don't draw any of the carbons or hydrogens in. We basically just draw like the mountain ranges, if you will. Any questions on that there? As we're talking a little bit about formulas here, we also could write a formula in organic chemistry, which is sometimes referred to as the condensed formula, which looks something like this. This is what is referred to as the condensed structural formula. It is the condensed structural formula because I put dashes in between the guys. But basically the difference between this guy and this guy is on the guy on the top there, you draw out the hydrogens. The guy on the bottom, you don't draw out the hydrogens. Now, even though it's connected like this, the connectivity is still carbon to carbon, and the hydrogens are still attached to each of the carbons. So in a condensed formula, even though it may appear that the carbon and hydrogens are attached to each other, it's actually still this carbon to carbon arrangement that is attached. Any questions on that there? Now, when we get to carbon that can make a double bond, for example, what happens here is a couple of things. We end up with something like this. By the way, if we looked at the guy that had the single bond, which was our alkane, it looked like this. When I put on that second bond to make the double bond, what did I lose on each carbon? I lost a hydrogen. So typically every time in organic chemistry, you need to put on another bond to make a double bond, a triple bond. You will lose a hydrogen from each carbon. Otherwise, if you don't do that, the carbon has way too many bonds attached to it. So you do lose a hydrogen on each one every time you do that. So as you go from the alkane, which is a single bond, you move to this guy, which is known as an alkene, which has a functional group of a carbon-carbon double bond, basically. Again, we sacrifice the hydrogen on each one to make that double bond. It also does change some of our geometry here. Now, when I look at this carbon here, it has how many electron pairs? It has 1 electron pair, 2 electron pairs, and our double bond counts as only 1. So it actually has 3 electron pairs. Same thing with bonds. It has the 1 bond here, the 2 bonds here. And once again, our double bond will only count as 1 bond, which would be 3 bonds. That is our good friend trigonal planar, yeah, our triangular. That has a bond angle of a $120, yeah, in terms of that, 120 degrees. That is because it technically makes a triangle, yeah. Makes a nice equilateral triangle sort of happening there. Now, in this case, the hybridization of that carbon would be, what would be the hybridization here? It has 3 electron pairs, 1, 2, and 3. That's an S and 2 Ps. That is an sp2 hybridized carbon, is basically what you got going on there. Now, if we draw something that does have a double bond in it, you could also draw it, you know, a couple of ways. You could draw it just, again, inserting the double bond in there like that without worrying too much about the sort of geometry of it. But when you do insert that double bond, this carbon right here will have 3 lines coming in. It actually only has 1 hydrogen. This carbon here would have 1 hydrogen. This carbon here would still have 3 hydrogens. And this carbon here would have 2 hydrogens. And this guy would have 3. Again, you typically do not draw the hydrogens when you do line structure. Again, you would just draw something like that. So the carbon that has 4 bonds is really important. Again, pretty much in organic chemistry, if you're drawing something and you're out of elements and you need to finish your picture, you basically just lay up some hydrogens to get carbon to 4 bonds, and you will have, you know, basically what you need. Any questions on that there? The tetrahedral is sp3, yeah. And that's what you'll see in, that's what you see with the alkanes. And that's, again, why they're also really drawn like that in line structure, and what's sometimes referred to, again, as that zigzag shape, because as it goes tetrahedral to tetrahedral, kind of goes up and down and stuff like that. Other questions? Now, another way carbon can make a bond is obviously very common, which is a triple bond. Once again, here, if you look between this and the alkene that we just had, we are again going to sacrifice another couple of hydrogens there to make that extra bond in there, so we don't end up with too many bonds to carbon. This guy is what is known as an alkyne. That is not spelled like that. Let's try that again. Alkyne. There we go. There we go. So this is an alkyne. The functional group of an alkyne is a carbon-carbon triple bond. And once again here, by having that triple bond happening there, it is going to change a couple of things in terms of the carbon. If we look at our carbon here, it has 1 electron pair. And once again, our triple bond here will only count as 1 electron pair. So that is 2 electron pairs. Also, it'd have 1 bond, and the triple bond would count as 1 bond, which would be 2 bonds. So that is our good friend linear, is the geometry that we have going on there. It basically straightens out to 180 degrees. So technically speaking, if you draw your kind of guy, your triple bond will sort of straighten out there at the end. There technically would be a carbon at the end here. There would be a carbon right there, carbon there, carbon there, carbon there, and carbon there. And this guy would have 1 hydrogen. The guy here would actually have no hydrogens, as it has 4 bonds. This guy would have 2 hydrogens. This guy would have 2 hydrogens. This guy will have 2 hydrogens, and this guy would have 3 hydrogens. Once again, if you're not super concerned about sort of the geometry, you could just draw it as commonly drawn, just like that, kind of laying up the triple bond in the middle, even keeping kind of the zigzag shape. Even though in reality, that part of the molecule would straighten out into linear as well. So in terms of the hybridization here, if we were to go through our little guy here, it has basically 2 electron pairs, which is 1 and 2. So that's an S and a P hybridization that would happen here for that carbon. By the way, we don't get into the dehybridization until you get into what type of geometries. SP3D1 is triangular bipyramidal, the exception to the octet rule, the expanded octet, 5 electron pairs. And SP3D2 is octahedral, which has 6 electron pairs. Usually don't run into too much of that in organic chemistry, but that is, how you would get into the D guys, is those expanded octets that you see with guys on the periodic table of where sulfur is to the left, to the right, and down, that have the ability to do that. Any questions on how to identify hybridization, geometry for these guys? Yeah. What's that? No? Question? No? Good. Okay. Yeah. Well, so the condensed form for, say, something like this, it actually would just be, I scribbled over it. Let me just kind of redraw what we got going on here. You could do something like this. Here, I'll add an extra one to it. So you would just do the same thing. You basically just take each of these segments where the carbon is. So that would be CH2, CH2, and CH3, something like that. And then for the triple bond, we could do this one here. That's a carbon, 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 carbon. So basically this guy would be CH3, CH2. This guy would then be just a C, a triple bond, also to a C, and then off to a CH2, CH2, and CH3 in that case, yeah. So those would be the condensed ones. Other questions on that? Okay, so those are some of the functional groups that carbon makes and the bonds that they make and the importance of some of those bonds. Methane is a main component of natural gas. It's the stuff that comes out of our pipes here when we light a Bunsen burner, which I believe we never did this semester. Good chemistry class when you never light a Bunsen burner. Ethylene is used to make some plastic. Propane, as I mentioned before, is a alkane. They're all single bonded. Sometimes though, they do make sort of ring structures. So this right here is what's known as cyclopropane. If we just draw it in line structure, it's a triangle. But at each of these corners is a carbon. And once again, to get carbon to 4 bonds, each of these guys would have hydrogens, as you can see there. So sometimes what will happen is, this is what is sometimes referred to as the straight chain, which basically means it just runs in a straight line. This is what is sometimes referred to as a cyclic structure, which means they can basically turn up into a ring type structure. And there also is, as we'll see, what are sometimes referred to, and I won't draw the hydrogens, what is sometimes referred to as like branch chains. So this is sometimes what is referred to as a branch chain. Obviously, all those guys would have the appropriate hydrogens, but it's like a tree. There's like a main, obviously, part of the tree, and then off of that main part are some branches that are basically hanging off. So that is also what you sometimes will see. Now, organic chemistry, as I mentioned, is the basis of it. In most organic molecules, the backbone is the carbon-carbon bond and the carbon-hydrogen bond. But as we really do sort of swap out some of the hydrogens for some other elements, we do get some different sort of organic compounds. And very commonly, halogens find their way into organic compounds, nitrogens, oxygens, sulfurs are very, very common, find their way. For example, most of the functional groups, a lot of them will have oxygen in there, and there's a couple of major functional groups that have nitrogen as part of it. And again, some of them will have some of the halogens incorporated in there. As we do change from sort of all carbons and hydrogens, it does change some of the properties that we see with particular molecules. It does give some molecules some ability to interact with polar things like water. So some molecules, some organic molecules do have the ability to basically be soluble in water because of some of the functional groups that they have, especially ones with oxygen and hydrogen. So these are common sort of arrangements of some other groups that end up there. That's a very common arrangement for oxygen. Also, the carbon kind of double bonded oxygen is what is referred to as a carbonyl group, is a very popular sort of bond that you see in organic chemistry. The OH group as well, also very commonly seen. So for example, if we do swap out something, say on an alkane, one of those hydrogens for like an OH group, this OH group is the functional group for an alcohol. So if you see an alcohol, that is basically its functional group, which is the OH group. And that OH group is a polar group with the oxygen being more negative, hydrogen being more positive, and that hydrogen is directly attached to an oxygen, which means it can hydrogen bond. So that OH group has the ability to hydrogen bond. So really in this molecule here, which is ethanol, it really has two parts. It has this part here, which is really the non-polar part of the molecule. But it does have this part up front here, which is polar. And because it does contain this polar group, it actually is very soluble in water. So it's able to interact with water. I'll just draw out the last part here. Through hydrogen bonding. So when it comes across a water, which has a negative oxygen, a positive hydrogen, this has a positive hydrogen and negative oxygen, boom, they're able to hydrogen bond with each other. And because they're able to hydrogen bond with each other, that makes them really soluble in water. So something like ethanol, which has like two carbons, something like methanol, which has one carbon and an OH group, will be soluble in water because they have the ability to hydrogen bond. Now, there is usually a pretty common rule in organic chemistry. If you do have this sort of functional group that has the ability to hydrogen bond or that is polar, it is usually fairly soluble in water, but solubility decreases a lot when you build out the carbon part of the molecule. So as the carbon part of the molecule or the nonpolar part of the molecule gets larger, so for example, this part of it, if we built out a bunch more carbons, the solubility pretty much drops to nothing. So if you took the same sort of arrangement, but you had like, a ton of carbons leading into that OH group. I'll do that since I'm out of room. But basically here, we have now this giant part of the molecule here that is nonpolar. We have this small little part over here that is polar. And what happens is, frankly, this part gets in the way. of water being able to get in there and interact well. It's what is sometimes referred to as steric hindrance. It basically gets in the way of allowing those guys to get in there. In addition, that molecule that I just drew there is also quite large. And if you think about things being able to be soluble in water, they basically need to replace water interactions with other water interactions with similar type of interactions, which means if you try to fit a really big molecule in there with water, it is not going to work. And it has this really big non-polar part, which is just going to get in the way of the interaction. So usually in organic chemistry, once you hit about 5-ish or 6 carbons, even if that molecule has a polar group on it, solubility pretty much drops off to nothing. But if it does have a polar group and it's usually less than 5-ish carbons or so, it usually will be fairly soluble because it doesn't get in the way and they're able to really hydrogen bond, for example, with something like water. Any questions on that there? So as I mentioned, here are a couple of very common arrangements for carbon and oxygen. Carbon single bonded into the OH group, and this guy right here, which again is a carbonyl group. This carbonyl group, by the way, is a polar group, carbon being more positive, oxygen being more negative, and that's really important in how mechanisms occur in organic chemistry. Most mechanisms, as you'll learn, for reactions occur through like a positive negative sort of attraction. The negative guy goes attacks the positive carbon. It ends up breaking some bonds and allowing things to move around. And a lot of organic mechanisms are the basis of like something that's negative comes in, breaks these bonds, and allows the whole reaction to sort of take place. So most reactions, as I mentioned, do occur at the sort of functional group. As we talked about some of the structures already, this again is condensed formula where we just don't draw out the hydrogens. A lot of times though, people will still, although they didn't do it in this one, will still kind of put the kind of bonds between them as well. Also, a lot of times when people are drawing condensed formulas and there may be something else attached, you know, they'll kind of show it like that as well. And kind of draw a second line up above it in the condensed sort of formula. All right, as you can see there. I would say not too often people kind of do condensed formula like that because sometimes it gets confusing for people. Most of the time people will kind of do condensed formula like that. If you have a couple groups at the end, they'll really draw the line and kind of put it in there. The skeletal formula really is the line structure. And again, line structure is used obviously a lot in organic chemistry. And it just makes it a little bit neater. As you can see on the left there, if you draw out all the hydrogens and stuff, it's really crowded. So very commonly, we do use line structures a lot. This would be 6 carbons, as you can see over here. This is what is known as cyclohexane. It is a ring type structure. By the way, to close this thing into a ring, it also loses a couple of hydrogens to allow it to close in a cyclic manner. And that's a skeletal structure there. If there's something off of a ring type structure, they will draw the group there as well. By the way, in sort of line structure, if there is something meant to be at the end of the line, they will put something there. If you just see a lonely line like I just drew there, it is meant to be a carbon at the end, and it would then have 3 hydrogens. So sometimes people get confused, like I see like a line drawn, but there's like nothing at the end of the line. What's there? So what is there is basically just a carbon with the appropriate number of hydrogens. Again, if they wanted something else there, they definitely would write it in if it is not carbon. So in line structure, if you see a lonely line, it's not just a lonely line, it's actually this guy at the end of the lonely line. And again, if nothing else is there, then you definitely will not see it. Now, as I mentioned before, really organic chemistry can be broken up into different types of organic molecules, and they really are based on the functional group that's present. The functional group is really the part of the atom where pretty much all the action occurs, and it pretty much is what gives that organic molecule its type of properties. So like we just saw there with the alcohol, the OH group gives the alcohol some polarity. And any type of reaction that occurs with an alcohol will occur right there near that OH group, and the OH group would be involved in it. Sometimes R is used as a shorthand in organic chemistry, and basically R just means it's a carbon group. Could be 1 carbon, 2 carbons, 3 carbons, but there's some type of carbon attached to it, and obviously the functional group tells you the certain part. So if you see like an ROH, that basically means this R is a bunch of carbons attached to an OH group, which makes it an alcohol. See that? Now, hydrocarbons are compounds that contain, much like the name implies, only hydrogen and carbon. Alkanes have only carbon-carbon single bonds, which we talked about. Alkenes have carbon-carbon double bonds, which is our functional group. So carbon-carbon single bond, carbon-carbon double bond, and our alkyne is a carbon-carbon triple bond. There's also a class of organic compounds which are known as aromatics. Aromatic compounds are all based off of benzene, and benzene looks something like this. It is a 6-carbon ring that has 3 double bonds, sometimes drawn like that. You could also do a resonance structure where the double bonds move to the other side. And in fake organic, not real organic, a lot of times they will also draw, just say, no, they'll do it in each. They'll sometimes just draw like a little circle in the middle to indicate that those double bond electrons are moving around, they're delocalized. So you'll see that as all 3 representations of a benzene ring. So that is not to be confused with this ring here, which has no double bonds. That is what is known as cyclohexane, which is not benzene. So benzene needs to have the double bonds. By the way, when it has the double bonds, that means each of these carbons pretty much has just 1 hydrogen attached to get it to 4 bonds. So it's basically C6H6 is the formula there for benzene. Questions or anything? So let's take a look at some of the different functional groups that are in organic chemistry. So obviously we talked about the alkane, which is the carbon-carbon single bond. By the way, alkanes have a general form of CnH2n plus 2. That is how many carbons there are, which is N, and how many hydrogens should go with it. Our alkene has the carbon-carbon double bond. Again, we talked about the hybridization there, going from sp3 in the alkane to sp2 in the alkene to our sp in our alkyne. And there is our aromatic compound, or our benzene ring. Some other important organic functional groups is what is referred to as an alkyl halide. I'll spit that out. Alkyl, I can't say that today, but that word right there basically means carbon. Yeah, so it's like carbon containing group. And halide is a halogen, yeah, that has a negative charge. Yes, like F minus, Cl minus, Br minus. So alkyl halides are basically a alkane that has a halogen attached to it. Alcohols, as we saw, the functional group being the OH. The ether is a carbon, oxygen, carbon functional group. The amine has a nitrogen containing group. It is very similar to ammonia. So there are basically ammonia derivatives. Thiols are stinky because they have sulfur. They are the SH group is the functional group there. So these are the different parts of the molecules that give it. Once again, as I talked about earlier, something with an alcohol has the ability to hydrogen bond. So again, it has a little bit of solubility. By the way, this guy as well, because that is a hydrogen attached to a nitrogen, right? Just like ammonia, NH3 can hydrogen bond, so can amines hydrogen bond as well. So it also has the ability to hydrogen bond. And this guy here doesn't have the ability to hydrogen bond, but it can do some polar bonding as well. As I mentioned, this is a very common part of a number of functional groups in organic chemistry, which is this carbonyl carbon or carbonyl group. Again, it is a polar group there where the carbon is more positive, oxygen is more negative. That also helps in some cases with solubility and the ability to sort of hydrogen bond. Although it cannot hydrogen bond itself, it does have the negative oxygen, which perhaps could participate with a little bit of hydrogen bonding in something like water, depending on what compound you're dealing with. There are several organic groups that contain these. Aldehydes, the functional group for an aldehyde is the carbon-carbon oxygen double bond and the hydrogen. You will always find this group at the end of a molecule. So the functional group for an aldehyde should always be at the end. Why will it always be at the end? It will always be at the end because it has a hydrogen. Hydrogen should have how many electrons? It should only have 2 electrons in a bond, right? And when it's bonded, that means that if you put it in the middle, it's going to have way more than 2 electrons. So because it has a hydrogen at the end, that functional group will always be at the end of the molecule, one end or the other. This is a ketone, which is a 3-carbon run you need. And in the middle of that 3-carbon run, you have the carbon-oxygen double bond. So a ketone basically has that 3-carbon run. With that, by the way, if you're drawing some line structure, you just draw these like normal. You would do like a double bond there, and you would actually put the hydrogen at the end, and that would be our carbon and our functional group for our aldehyde. If you were doing sort of line structure for a ketone, you draw something like that, and that would give you your carbon, carbon, carbon with our double bond there in the middle of that 3-carbon run. Some other ones that have this double bonded oxygen is a carboxylic acid. That is this guy. You might be familiar with a carboxylic acid. We use this guy. This guy is what? This guy is acetic acid. Yeah. Vinegar, also known as ethanoic acid. That's basically what we did titrations with. So that is basically acetic acid. That is the functional group right there, right? Which is our carboxylic acid group. This is what makes it an acid. It's actually that bond right there. That OH is the H is going to come off when it does it. And once again, if you were to sort of draw this as well, you would do it like that, and that would be your functional group right there. Look something like that. An ester is a fun one, I guess. It is a carbon oxygen double bond to an oxygen, which is usually attached to a carbon. Esters are made from basically combining a carboxylic acid with an alcohol. You basically take water out and you squish them together. The beauty of esters is they are responsible for a lot of things that smell, like, banana smell, pears, all those type of things that have like aromas. A lot of esters are responsible for a lot of common smells of food and stuff that we actually smell and be able to recognize, obviously, foods as. An amide is a nitrogen containing group, which is made of a carboxylic acid basically and an amine that come together, and it has the functional group of the carbon oxygen double bond into a nitrogen. Yeah. So that is like basically the bond there. And that bond as well is seen in amino acids. Yes, peptide bond is basically that amide bond is what you get there. When you take your amino acids and you stick them together in primary structure and you take out water, you basically put those guys together and you get this amide bond. Any questions on that there? So those are the different functional groups. You should be familiar with the different functional groups because it will be in the experiment that you need to do and identify those different functional groups. We're not going to talk about obviously all of them in more specifics, but those are sort of an overview of all the different types of categories of functional groups. Any questions on any of that there? Okay, so let's talk a little bit about some of these groups here in a little bit more detail. The alkanes, as we talked about, are really the simplest organic molecules you could have. They basically all have that carbon-carbon single bond. Alkanes contain carbon atoms and no rings. They're sometimes referred to as acyclic alkanes. As I mentioned before, they have the general formula of CnH2n plus 2. What that means is if I have one carbon, N is 1, so 2 times 1 is 2 plus 2 means it should have 4 hydrogens. That is what is known as methane. If I have 2 carbons, N is 2, 2 times 2 is 4, plus 2 is 6. It should have 6 hydrogens. That is what is known as ethane. If I have 3 carbons, 3 times 2 is 6, plus 2 more is 8 hydrogens. That is what is known as propane. And you might see a pattern here. These all end in ANE, just like the alkane name ends in ANE. And that is really how you know they're alkanes. C4H10 would be butane. C5H12 will be pentane. Why not? I got an empty spot on the other side. We'll continue down. C6H14 would be our friend hexane. C7H16 would be heptane. C8H18 would be octane. C9H20 will be nonane, perhaps. Could be making this up, maybe. C10H22 would be our friend decane. Now, there is a reason why I wrote all 10 of those names, and we'll see it again on another slide. The reason is, if you want to do well in organic chemistry, you should learn those names and how many carbons there are as soon as possible, because frankly, everything in organic chemistry pretty much comes back to these 10 names. There are some more without that, but a lot of it really is based off of these first 10 names. A lot of all those other functional groups that we saw, their names and how you derive their names really come from the alkane name. So the alkanes are really the basis of pretty much all those other functional groups that we saw. And the first 10 are kind of important. You really can basically derive everybody's name, from those guys as to how you get there. Now, when we do have alkanes, because they are all single bonded, that means that the carbons have the maximum number of hydrogens that they should, and that is what is referred to as being a saturated hydrocarbon. Saturated means that the carbon atom pretty much has the maximum number of hydrogens that it should contain. And that always occurs in alkanes because frankly, they're all single bonded. You only start to lose hydrogens when you make like a double bond or a triple bond. And those are what are referred to as being unsaturated hydrocarbons, because they have not the maximum number of hydrogens, because you have to basically sacrifice those. Cycloalkanes are when those guys are joined together. And in a cycloalkane, they have a general formula of CnH2n. They lose 2 hydrogens when they fold up into the ring structure. So for example, if we look at propane, which is this guy here, when it becomes the cyclopropane, which is how we would name it. This is propane. This is a ring structure which becomes cyclopropane. It now has a carbon, 2 hydrogens there, carbon, 2 hydrogens there, and a carbon, 2 hydrogens there. It loses basically a hydrogen to close up on each other on each of those carbons. So that is why it actually will have 2 less hydrogens. We basically put cyclo in front of it, and it's basically the ANE name. Now, just to illustrate what I was talking about in terms of the first 10 alkanes, if we did take something like, by the way, this right here, the IUPAC, is a name that you see a lot in organic chemistry. It's the International Union of Pure and Applied Chemistry. They are the three guys in a room that you could thank for like how you name everything and all the crazy ways that you name everything. So usually in organic chemistry, you oftentimes hear give me the IUPAC name. That's like the official way that you're supposed to name things. One thing that you'll learn about organic chemistry if you take it is you pretty much have multiple names for like the same compound. There's like the IUPAC way of naming things. There's sort of common names that people use, and there is like historical names that people still use. So for example, this guy here, this guy here is what is known as 2-propanol. It's also known as isopropyl alcohol. And it's also known as rubbing alcohol, yeah? All the same thing, basically. So there's a lot of common names, historical names that are used. Like we saw with acetic acid is very much called acetic acid. Its IUPAC name is ethanoic acid, and people oftentimes will call it vinegar because it's the major component of vinegar. So a lot of times in organic chemistry, there's a lot of sort of, we're looking at the same compound, but we're calling it different names, and that happens a lot. Now, to illustrate what I was talking about a second ago, you could have something, would take something like this guy here. This is 2 carbons, which is ethane. This is 2 carbons with a double bond, which is an alkene. That is ethene, E-N-E. This is 2 carbons with a triple bond. That is ethyne. This is 2 carbons with an aldehyde group, ethanal. This is 2 carbons with an OH group, ethanol, yeah, and so forth. We have our 2 carbons that we saw there with a carboxylic acid group, ethanoic acid. So if you can't see where it all comes from the alkane name. And these are all different types of organic guys. This guy is an alkene, E-N-E. That's how that name ends. This guy is an alkyne, Y-N-E. That's how that name ends. This is an aldehyde, not how that name ends, but that is an Al. This is an alcohol, O-L. That's how that name ends. This is a carboxylic acid. These are all different organic compounds, but the basis of how you name pretty much all organic compounds is what is the longest number of carbons there are, and they all go back to the alkane name, and you change a little part of the name based on the functional group that is there, and that's why it's really important to learn those alkane names, because really everything is sort of based off of that. Any questions on that there? Okay. So some simple alkanes. Again, methane is pretty much the simplest organic molecule you could have. Basically, it has 1 carbon and 4 hydrogens. Ethane, again, has our 2 carbons. Propane has our 3 carbons. And when we talk about propane and how you draw it, sometimes people think when you draw things and you kind of move them around, you're drawing something different. And there are things that can have the same molecular formula, but different connectivity. Those guys are what are referred to as isomers. So isomers are things that have the same molecular formula, but have a different connectivity. So for example, here, we always want to look for the longest continuous carbon chain. That is 3 carbons. And although the guy over here on the right may look different to you, if you count the longest continuous carbon chain, it is still 3 carbons. So both of these guys are propane, even though they may appear different to you. Now, if we look at something, say like C5H12, and we wanted to draw some isomers, right? Well, we can go carbon, 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 all in a row. And we'll put in our hydrogens here to get to 4 for each of them. And that would be pentane. Right? Now, I could decide to do maybe just 4 carbons in a row and put another carbon there. Could do something like this. Could do 3 carbons in a row. Maybe do this. Now, if we count all these and I didn't screw up, hopefully not, we'll hope for our best here. But they all should have basically 5 carbons, I hope, and they all should have 12 hydrogens there. So technically, you may look at all these and go, they all look different. They're all isomers of each other, right? And to know whether or not they really are isomers of each other is a good way to do it is to try to actually name them. And if you name them and you get a different name, then they are isomers of each other. If you name them and you end up with the same name, then they frankly are not isomers of each other. You just drew it looking different. I guess the key to that is to make sure you properly name it. So let's talk a little bit of how do we go about naming these guys, alkanes. Always, pretty much all organic naming always starts with finding the longest carbon chain. And that is a continuous carbon chain where you start in one direction, you go to another direction until you hit a dead end. The only thing you cannot do is back up. So you got to go one way until you hit a dead end and then you got to stop. The longest continuous carbon chain does not necessarily mean it has to be the straightest carbon chain. It could go straight, go up, go over, maybe come back down, maybe go that way. So you do want to think about all of your options. Once you find the longest continuous carbon chain, that would be the base of your name. And it should match an alkane name, right? So you got like 3 carbons, it's propane. You got like 4 carbons, it's butane. Anything that is not part of the longest continuous carbon chain, anything not part of that chain, is what is known as a group that's attached. So those are groups that are attached that are not part of it. If they are carbon-based groups, they are also based off of the alkane name. So come here for a second. To illustrate that, for example, if we look at methane, if I wanted to say I had a chain of carbons coming through here, and I wanted to attach that methane into this spot, can I do it the way it is with all 4 hydrogens? I could not, because then carbon would end up with 5 bonds. So in order to allow a group to attach, it's got to give up a hydrogen to allow it to attach. So when it attaches, it's not going to attach as methane with 4 hydrogens. It's going to attach with only 3 hydrogens. But it is based off of methane because it has 1 carbon. And this is what is referred to as an alkyl group. The alkyl ends in YL, which means instead of this now becomes a methyl group based off of methane, which ends in YL. If I had an ethane, once again, if I wanted to slap my ethane into that opening there, I could not do that for the same reason, because there is too many hydrogens. So if I take off a hydrogen from ethane, it will allow it a place to attach to the group that will not make it have too many bonds. And because it's based off of 2 carbons, which is ethane, this is what is known as a ethyl group. So again, you can see even the groups that are attached that are carbon based are based off of the alkane names, which is why it's really important, those names. By the way, groups could also be like a halogen. So you could have a group that's a halogen, like Br minus, F minus, Cl minus. These are named very much like what we talked about when we were doing coordination compounds. So fluoral for fluorine, chloral for chlorine, bromol for bromine. So it's the same type of naming that we had before. Any questions on that? Now, there are some groups that have special names, and this, for example, is a very common one. It actually connects here, and that is what is known as isopropyl group. And that's different than a propyl group that would attach at the end. So it would attach at the end. This is just a propyl group. So what is the difference? The difference is in the carbon at which it is attaching. You can classify carbons in organic chemistry as primary carbons, secondary carbons, or tertiary carbons. So if you look at a carbon, for example, this stuff here. So if you look at a carbon that is attached to one other carbon, this carbon right here is what is known as a primary carbon, because frankly, it is attached to one other carbon. It's pretty much the easy way to do that. If you have a carbon that is attached to 2 other carbons, this carbon here would be a secondary carbon. And if you have a carbon that is attached to 3 other carbons, this carbon here is a tertiary carbon. And identifying things as primary, secondary, tertiary is very common in organic chemistry. I personally like to do it this way by counting carbons. Some people count hydrogens, how many hydrogens there are. There's 1 hydrogen, 2 hydrogens. I think just counting the carbons is much easier, because however many carbons you have is what it is, primary, secondary, tertiary. If you count hydrogens, you got to go backwards. You got 3 hydrogens as primary and so forth. So some people will do the hydrogen counting versus the carbon counting. Now, how that affects something like propane, if we look at propane, this carbon right here would be a primary, secondary, tertiary. That carbon would be a primary, as it's attached to just 1 carbon. The carbon in the middle would be a secondary carbon, as it's attached to 2 carbons. Primary at the other end would be a primary carbon. So where the hydrogen is lost in some of these groups gives you some groups some different names. The attachment in a normal propyl group happens at the primary carbon at one end or the other. The attachment happens here at the primary carbon, and that gives you a normal propyl group. But if you take the attachment in the secondary carbon, that gives you what is known as isopropyl. So there are other groups like sec-butyl, sec meaning secondary is where the attachment happens. There's one known as T-butyl, which is tertiary, which is where the attachment happens. So sometimes the groups have some special names based on where the attachment actually happens. Any questions on that? That's a nice side trip to explain. Now we'll go back to the naming part of that. So again, any of those guys that are not part of the main chain are referred to as groups. Once you identify the group names, the next thing that you want to do is actually number the carbon chain. And when you number the carbon chain, you always want to number, in the case of alkanes, to give the groups the smaller number. So whatever groups are attached should always get the smaller number. You want the groups here for alkanes to get the smaller number. Now that does change when you get into other functional groups like alcohols, aldehydes. You want to actually give the functional group the smaller number, but for alkanes, it's actually the groups that are attached that get the smaller number. You need to give the number of where the groups are attached to the what carbon. And you do put them in alphabetical order. The last thing is, if you have a number, it is separated from a letter by a dash. And if you have two numbers in the name, it is separated by a comma. Now that I'm tired, let's go through this here. There we go. So longest carbon chain here on the first one, pretty easy to see. It is 5 in a row, and 5 in a row is pentane. Longest carbon chain on the second one I drew is how many? It is 4, and you could also get it, in this case, the straightest way. It would be these 4 here. If you went this way and went up, that would be 3, and that's obviously less than 4. So because the longest continuous carbon chain here is 4 carbons, 4 carbons is based off of the name butane, would be the base of the name. Now, attached to those 4 carbons is now a 1 carbon group. And because it has 1 carbon, it's based off of methane, and that would be known as a methyl group. So now we have our group, we have the base of our name. We need to number the carbons. There's 2 ways that you can number the longest carbon chain. You can number it going left to right, which would be 1, 2, 3, and 4. You could also go the other way, right to left, which would be 1, 2, 3, and 4. Which way gives the methyl the smaller number? Going left to right. If you go left to right, the methyl group there is at carbon number 2. If you go right to left, the carbon is at number 3. So the way that we would want to number is actually going in this direction, as it gives the group the smaller number. So that means that guy is at a 2-methyl. Now we got pretty much our entire name. We can put it together. 2-methyl, and it is butane. The 2-methyl butane. That name, which is properly named, is different than this name, which means those 2 guys are isomers of each other. Yeah, they have different names. They're different things. They will have different properties. First off, any question on that one there? How about this one? The guy on the left, longest carbon chain is 5, which means there's nothing else attached but that longest carbon chain, which means this name is pentane. So even though it looks different, is that one the first one isomers? These 2 guys are not isomers. They're the same thing. You just drew it different to kind of make it look like an isomer, but they are not isomers of each other. And that's very common when people are asked to draw isomers. They just kind of, I'm just going to kind of draw this part up, this part down. It looks different, but it's really not different. It is the same molecule. How about the last guy that I drew? Longest carbon chain is? It is 3. You could get it multiple ways. You could go this way. You could go this way and up. You could go this way and down. By the way, if there are multiple ways to get the same longest carbon chain, it doesn't matter. You can choose either way you want. Those should all come out the same name at the end. So since the longest carbon chain here is 3, the base of my name is going to be propane because that's 3 carbons. I then have attached to that a methyl group there and a methyl group there. So that is 2 methyl groups in the same compound. So very much like what we talked about when we did the coordination naming, when you have 2 groups that are the same, we actually use a prefix. So this would be what is known as dimethyl. The di is not because both methyl groups are on the same carbon, it's because there's just 2 methyl groups in the compound. They don't have to be on the same carbon to be dimethyl. If you had 3 methyl groups, it would be trimethyls. If you had 3 chloral groups, it would be trichloral. So we do use prefixes if you have more than one of the same group in the compound. Once again, it does not have to be on the same carbon. In this case, we do want to number. So our 2 ways of numbering is going left to right, which would be 1, 2, and 3. We also could go right to left, which would be 1, 2, and 3. Does it make a difference in this case? It doesn't. Both of those methyl groups are at carbon number 2. I'm going to go up here on top to write the name. You do need to give the number twice. So even though they're hanging out at the same carbon, you got to give the number twice. They're on different carbons. You would give different numbers, but you would do 2 numbers, which means I need a comma between those 2 numbers. So this would be what is known as 2, 2 dash between the number and the letter, dimethyl propane, which is obviously this guy down here. That name is different than pentane, which means that guy would be an isomer. So out of the 4 that I drew, these 3 are isomers of each other. The guy on the bottom left is not an isomer of each other. That was a long way to go to understand how to understand isomers. Any questions on the naming, isomers, any of those things? The one I put an X on? Is that what you're asking? The 2,2-dimethylpropane is an isomer. Yeah. Yeah. So in this case, if you were asked to say draw 3 isomers that had C5H12, you could draw this, you could draw this guy, and you could draw this guy. All 3 of those guys would be isomers of each other. They all contain 5 carbons and 12 hydrogens, but they have different connectivity, and they also will have some different properties because of that connectivity. So they are different molecules. The only one that would not be, if you drew all 4 of these, considered another isomer would be this one, because it's the exact same guy as this one. It's just drawn differently. So they're really the same thing. Yeah.